We're in section 6.2 today, which is properties of parallelograms. On our last set of notes, we really talked about lots of different types of polygons, and we talked about parallelogram, or we talked about quadrilaterals a little bit. We're going to kind of dive into a very specific type of quadrilateral today. We're going to focus on parallelograms.
Okay.
And when we look at this, I wanted to first define it because that's important that we know what we're talking about. And when we see the definition of a parallelogram, it's a quadrilateral, meaning that we are going to have how many sides?
4 sides.
So 4 sides. And within those 4 sides, we know that both pairs of opposite sides will be parallel, which sounds like it should make sense when we say a parallelogram. We're going to have some parallel pieces. So in this case, if I look at opposite sides being parallel, that would be referring to what?
Segment AD and segment BC are going to be parallel. And then segment AB and segment DC are going to be parallel.
Great. So we're going to have 2 sets of parallel sides. That's the definition. So if we were to be using this in a proof, kind of as a hint, because we are going to see a couple proofs, we would want, if we're given that it's a parallelogram, by definition, this is what we know, is that opposite sides are parallel.
And if I gave you opposite sides are parallel?
Then we could say that that is a parallelogram by definition.
Yeah, because definitions kind of go forward and backward. All right, now, notice the title says, and Ms. Hograby mentioned this, properties of parallelograms. So now we're going to kind of feed off of that. And I think already, I'm hoping at least, you're already thinking of things you already know. So you're looking at a parallelogram. You've dealt with a parallelogram before. And there's more to it than just the definition.
Right.
So I'm hoping some of this you already know, and then when you see it, you're like, oh, yeah, I know this. Okay, so the first property really is going to be a theorem. So the properties of parallelograms are theorems.
Yes,
okay?
they can all be proven.
These are all true things. Notice they all start with the if, okay, so a conditional statement. If you have a quadrilateral that is a parallelogram, so you already know you have a parallelogram, then what do you know? And in yellow here is kind of the key to this theorem, that opposite sides are congruent. So notice I already give you a parallelogram, so opposite sides are parallel based on that definition. But we also know that opposite sides are congruent. So which sides are going to be congruent?
So like AB is not only parallel to DC, it's also congruent to DC.
So I could say AB is congruent to segment DC because of this theorem.
Right.
All right. What else could you say?
I could also say that AD was congruent to BC.
So segment AD is congruent to segment BC. So this is all based on the fact that if you have a parallelogram. Now, something that we haven't done, and I'm going to make a note here, when you name a parallelogram, we often use a symbol for it, okay? Because parallelogram, it's kind of a long word, all right? Basically, just draw one. So do a little sketch of a parallelogram. So if I have parallelogram, not the best, it's kind of skipping on me, A, B, C, D, all right? And notice how I named it. I named it in that consecutive order. Okay, I can name this parallelogram CBAD if you wanted to. We talked about this yesterday. All right, so if parallelogram ABCD, all right, if you know that, then you can say that the opposite sides are congruent.
Perfect.
Okay, notice another thing, and I'm going to stress this because the next one's going to be the same way. It doesn't have a name.
No.
Now, that doesn't mean we're never going to use this. It's just we're going to have to explain it if I have to ever use it in a proof. So how I would explain it is kind of stressing this key ingredient. All right. So if you were using this in a proof, why do I know these sets are congruent? Well, because opposite sides are congruent.
And we know some abbreviations and some symbols to help us to condense that a little bit too.
Exactly.
So, like opposite OPP is fine with us. Opposite
Yeah.
sides, and then we know the congruent symbol.
Exactly. All right, so there's more theorems or properties of a parallelogram.
All right, this next one talks about the angles. It says, again, we already have to know that we have a quadrilateral and that it is a parallelogram. So you have to know you have a parallelogram first.
Okay.
All of these things kind of start off with that same idea of you have to know you have a quadrilateral that is a parallelogram.
Okay.
But then another thing that we're going to know is that the opposite angles are congruent. Okay, so if I know that we've got a quadrilateral, and how could I name this one?
ADBC.
ADBC. Again, notice they're not in alphabetical order, so just watch those. Quadrilateral parallelogram ABCD, ADBC, I can't even say it. If we know we already have that, then what do we know? What are the opposite angles they're talking about
angle A is going to be congruent to angle B, and angle D is congruent to angle C.
Right. So those opposite angles are going to be congruent to each other.
And I think most students know this idea in the last one. I think this is kind of a logical theorem because you've seen this before.
Right. One thing that I just want to clarify, it's not because they're corresponding angles. It's not because they're alternate interior angles. It's because we have a parallelogram. Those opposite angles are congruent. I'll every once in a while see kids that try to give me some of those things that we've learned about parallel lines before, but they're not necessarily true when I'm talking about these opposite angles. Now, I could talk about supplementary angles, which we're going to get to that in a minute, but be careful that we know that these are not talking about corresponding angles. And again, if I was using this as a reason in a theorem, this theorem as a reason in a proof, my brain is just tired today. I don't know. I would say that I know that these opposite angles are congruent because opposite angles congruent. So that would be my reason. That'd be kind of like our title of this theorem.
All right, so another one, and I think speaking of Ms. Hokerby kind of gave us a preview of where we were going. This is another one involving the angles of a parallelogram. So again, notice it starts the same way. I'm hoping you already are thinking, okay, if you already have a parallelogram, so if you know you have a parallelogram, what else do we know? Okay, well, they're saying in kind of the yellow here that the consecutive angles are supplementary. So if I have a parallelogram, how would you name this one?
Let's go DCEF.
So if you have parallelogram DCEF, then now they're saying the consecutive angles are supplementary.
Okay.
So which ones would be considered consecutive?
So consecutive we know is kind of like right in a row. So I'm saying like angle D and angle C are supplementary.
Are those the only pair?
No, then what about E and F? Oh, and I could even say like D and F also.
Angle D and angle F.
And angle C and angle E.
So there's quite a few. Because if you think about it, every angle is consecutive. Like angle D is consecutive to C, but it's also consecutive F. But that also kind of goes back to the last theorem. Well, these angle F and angle C are congruent, so if angle D is supplementary to C, well, angle D can be also supplementary to F in a sense, all right? This kind of can be elaborated on the idea of parallel, right? Thinking this one's a little easier to see. If these are parallel, all right, and this is the transversal, then these are consecutive interior angles, which means we know those are supplementary. So you could do that with any of these sets of consecutive angles.
So I could really say, based off of, if I had the parallels marked, I could use CIAT actually too.
And I like that you said that. You would have to first say the segments are parallel to use CIAT.
This, I just need to know it's parallelogram.
Yeah, what's nice, guys, think about it. The purpose of theorems is allow us to make shortcuts. So this allows us to jump right into this idea without proving parallel.
Perfect.
Because you already know it's a parallelogram. So just something to kind of keep in mind there. All right.
All right. This next one, wow, we've got a lot of these, don't we? All right, here we go. The next property or the next theorem based off of quadrilaterals being parallelograms. Again, the whole idea of all of these, we've got to have a parallelogram to start. The diagonals, which we talked about diagonals the other day too, going not to a consecutive vertice, but to a non-consecutive vertice. These diagonals are going to bisect each other. Now, what does it mean if they bisect each other?
That means you have some congruent stuff.
Right. So if I know here in this picture that I have a parallelogram, what do we want to call this one?
I'll call it JTPW.
Okay, so if we're given that we have a parallelogram, then what we can conclude here is that which pieces are being bisected. If diagonals bisect each other. So let's start with if JP is bisecting WT. If it's bisecting the segment, what does it mean?
Okay, that means, well, it says each other. So that means each diagonal. So like segment
Right.
JP is a diagonal. It's going to bisect the other diagonal, the WT.
Right.
So that means that segment TA is going to be congruent to segment AW.
Okay. But I love how you emphasize they bisect each other. Right?
So we're going to have another set of congruent. So what if I said WA or AW, whatever.
Yeah.
So what about if I have TW bisecting JP? Well, that means segment JA is going to be congruent to segment AP.
Right. Okay, so guys, what I want you guys to realize on this one, and again, we just say diagonals bisect each other, and diag is fine for that. All right. When you see this, this tells us that we have congruent parts. All right. Now, please be aware that they're bisecting each other. That it's not just one that's being bisected; it's both that are being bisected. So make sure that you've got both of those congruent statements that you've seen here. We've talked about diagonals a little bit before. We just haven't probably seen this in terms of parallelograms. This may be new.
All right. I think those are all the properties. So now we're going to apply them. So we have several examples. So starting off, it says MATH is a parallelogram. Okay, so when you see it's a parallelogram,
Nice.
automatically you know opposite sides are parallel by definition, but you also know
The properties.
all the different theorems. So opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, diagonals bisect, a ton of stuff.
Yes.
Okay, so it says find the following. Now, I'm going to add a little something to this because I know you're going to have to do this on a quiz or a test, is explain. All right, so justify where you're getting that. If that means you have to give a theorem as a reason, that's what I'm looking for. All right, so let's start off. So we're finding the measure of TH. Notice there's no segment bar. I've had lots of questions recently about when do I leave that on, off. So this is talking about the measure. So we're trying to find the length of this segment here.
Okay.
And notice, what is segment TH?
It is one of the sides of the parallelogram.
Okay, so we're probably going to need to know what. What do you think?
Well, I'm thinking we learned a property that said opposite sides are parallel, or opposite sides are congruent. So I know that MA was 8, so I think TH would also be 8.
You're exactly right. And what would be your reason for that?
Because opposite sides are congruent.
So this is what I mean by explain. Okay, it's not like you have to write a paragraph. It's super quick. It supports what you're thinking.
Okay.
All right, so let's move on. LH is the next length we're finding.
Okay.
So take a look at where that is.
That's part of the diagonal.
Okay.
And I remember we talked about diagonals bisect each other.
Good call.
And so as I'm looking at that MT, that segment is bisecting that diagonal AH. So I already have AL is 6. So then LH should also be 6.
Very good. And so my reason?
Diagonals bisect each other. Okay.
And notice how I said not just bisect, they bisect each other. What are they bisecting? Be specific.
Yeah.
All right. Now notice the rest of them are all dealing with finding angle measures.
Okay.
One thing to be careful, because I get this sometimes people make a mistake on these, is notice the order of the angle. Make sure you understand specifically what angle you're finding. So let's look at this first one. Angle ATH's measure. So that's this measure right here.
Right, so because T is the vertex. All right, so ATH. Oh, well, okay. I'm looking over at angle MAT because they gave us that as 105.
Okay.
And I remember we talked about consecutive angles are supplementary.
Okay. So what could we do?
So I could take 180 minus the 105, and that's going to give me my 75.
And the way to support that would be what you just said. The consecutive angles are supplementary.
Perfect. Okay.
So I might even label this.
Probably good.
And notice how I've been doing that, labeling as I go, because this is all one big problem. So it might be helpful to use that to find other things.
Okay.
All right, moving on. Angle THM's measure. So angle THM, so that's this one right here.
Okay. Oh, well, I see a couple ways I could actually talk about that one.
Okay.
Because I know it's also consecutive with the 75, so I
Okay.
could do the supplementary idea again, but I also have the opposite angle of 105. And I remember the property that said opposite angles were congruent.
So that probably to me would be quickest.
I think so too, because then I don't really have to show any work because I know that they're the same.
Okay. All right, moving on, and I might go ahead and label it. All right, so the next one, angle LMH. Sorry, angle LMH. That's this angle right here.
Okay, now I noticed that we've got a 40 degrees, and because the 40 is not on the line like our 105 was, that just must mean that it's the little part.
Okay.
And I know opposite angles are congruent, so that whole big angle together is 75, so the 40 is not talking about all of it.
And it wouldn't be, this is, I don't know if you've seen this in past, some students will want to say this is also 40 because they're thinking that they're bisected angles, but nowhere did we learn that.
No, it's only the diagonals that are bisected.
Okay, so she's kind of using a couple different things. So this whole thing is going to be 75, right?
Right. So I'm thinking like angle addition postulate almost.
Yeah. So you know that whole thing is 75. So to find the angle that's missing, LMH, you're basically doing 75 minus 40, right?
Perfect.
So this is 35 degrees. So a couple different things. She used this idea of opposite angles are congruent. She also used this idea of the angle addition postulate in a sense.
Right.
All right. Maybe label. Okay. Let's last piece. Angle ATM. Let's measure.
All right. ATM. Ooh. Well, okay, it's part of the 75, but I don't have the other part like I did on the other one. But, okay, could I go off of the idea of my parallel lines here?
Ah, I liking this idea.
All right. So I noticed that AT was parallel to MH. And I have that transversal of MT there. And when I draw that in, I notice that those angles, the angle that I'm looking for, and angle HMT, that angle there, are alternate interior angles.
And we know alternate interior angles are
congruent. So that's
that
also
means
35.
This is 35. And so my reason would be
AIAT.
Yeah. So this might be used because we knew that we had parallel as well.
Yeah.
Good. All right. So this is not like, there's not a lot of work, but the explaining part is justifying where you're getting it. So I know for a fact this would be a great quiz or test question. Just a little hint.
Yes. All right. Next one, find all angle measures. And I'm just going to underline that word all because a lot of times that's the piece that we forget too.
Yeah.
Okay. Looking at this picture, what is this a picture of?
It's a parallelogram.
And how did you know it was a parallelogram?
Because opposite sides are marked parallel.
Perfect. Okay. And looking at what they've given us, what property of parallelograms do you think
well, I see that the angles are labeled, and the angles that are labeled are the ones that are opposite, which means we're going to use the fact that opposite angles are congruent.
Okay. So if they're congruent, what do we know about these two values?
Their measures are going to be equal. So I can go ahead and set those values equal to each other.
Perfect. Okay. And then what would you do? Let's see.
All right.
Subtract our 3x, so x
equals 27.
Perfect. Now, is that all I had to do?
No, because you stressed we had to find all angle measures.
Yes.
So I'm going to take that value of x and substitute it back in. Let's say we find angle A first. So we'll do 3 times the 27, and then I'm going to add 18, and that gets you a 99-degree angle. So that's angle A's measure. But
Now,
I also know angle H is going to be the same thing.
Yes. Now, could we check it just to make sure we didn't make a little algebra mistake?
I think that would be a good idea, especially if you have time.
Right.
So do 4 times the 27 and add, or minus the 9, sorry, you also get 99.
You do. Okay. And so that's great. Those are the two angles that we were supposed to kind of find based off of the picture, but I still haven't found all angle measures yet.
Okay, and they don't have anything labeled on angle M and angle T, but I do know they're congruent. So I also know the other idea is that the consecutive angles are supplementary. So that means angle M and angle H are going to add up to 180. So if I do 180 minus the 99, I get 81. So that's angle M, and that's also going to be angle T. And a way to check is what should be true about all 4 angles.
Yeah, we learned that all of the angles of any quadrilateral, doesn't even have to just be a parallelogram, should all equal 360 degrees.
So they should add all up to 360.
And if you check that, they all do add up to equal 360 degrees. Awesome.
All right, so here's another one. And what are you seeing? What kind of, like, because we're talking about quadrilaterals, of course. That's the big focus. What do you notice about this quadrilateral?
Well, it is a parallel. The outside piece there is a parallelogram. We've got some triangles in there because they've drawn in the diagonals.
So the fact that you have a parallelogram, and the reason I think, and Ms. Hograby asked that question in the last one, I think because when we're moving on, we're going to learn other types of other parallelograms or other quadrilaterals. So knowing what kind of figure it is important to know first.
Right.
Because then otherwise you don't know what property you're going to use. So we're trying to find the value of WT and TQ. So we're trying to find the measurement of those two segments.
Okay.
And I like that you said diagonals are drawn in here. So the fact that we're dealing with a parallelogram and diagonals, we're probably going to be thinking, what do we know about the diagonals?
Right, and we know that the diagonals bisect each other.
So that essentially means that this segment BT is congruent to segment
TQ.
And then WT is congruent to
TY.
So notice the two of the pieces that we're trying to find are parts of some congruent pieces.
Right.
So let's find WT first. Probably doesn't matter.
Sure, yeah.
Okay, so if we're finding WT, we're going to have to find what to find WT?
Well, I'm really going to have to figure out what X is first.
Yes, and how are we going to do that?
I noticed that we said those two pieces are congruent. So 2X plus 2 should equal our 5X minus 10 because we know if they're congruent, their measures are the same.
Okay. So when I go and solve this, this is going to be what? 12 equals 3x.
3x and yeah.
So x equals
4.
4. Am I done?
No, because they wanted WT.
All right. So to find WT, I'm going to do...
So 2 times 4 plus 2.
So that is
10.
Now, if I wanted to check, because you mentioned this on the last one, what could I do to check this problem?
I could make sure that the 5 times my 4 minus 10 is also going to get me to
5 times 4 is 20. 20 minus 10 is also 10. So that works out.
Right.
Okay, so we got one piece down. Let's move on to TQ.
Okay. So for TQ, now I'm dealing with the stuff with R, so I'm going to solve for R first.
Okay.
I know that those two things should be congruent, therefore their measures should be equal. So R plus 11 is equal to 3R minus 15. So 2R equals, 20, we're working backwards. R is 12.
And now I have to probably substitute that back in.
Right, because that's just R, and we're supposed to find TQ. So 3 times R12 minus the 15. So that's going to give us, let's see, 36 minus 15 would be 21. Mm-hmm.
Now, you could also, if you wanted to, put 12 in for R here into BT, and then do 12 plus 11, which is also 21.
Right.
Okay, either way. But again, it's really asking yourself, what is it we have? What are we dealing with? And it's a lot of algebra.
Yeah. The big thing today is just knowing the properties.
Exactly.
If you know the properties, you're going to be fine.
You're going to be fine.
All right. Oh, you guys thought we were kind of done with proofs, didn't you?
We haven't seen proofs in a while.
We haven't. It's been a little while. All right. We are going to be doing a proof today. And we're going to be doing a couple proofs. Yeah. And they're dealing with the idea of parallelograms. So we're going to be using these properties to help support what we know.
Okay.
All right. So we know that we've got a parallelogram. And instead of writing out that big long word, I'm going to use the symbol A, B, C, D. So when you see that, given that it's a parallelogram, that means we have a parallelogram.
Good deal. Which basically means we could use definition. We could use any of those theorems. It just all depends on what you're wanting to prove, in a sense.
Right. Okay, so I want you to look at what you are given in this picture.
Okay.
In the picture. That might be something you want to maybe take a look at.
Okay, well, I'm trying to prove angle 2 and angle 4 are congruent. And I noticed those angles are not actually inside that parallelogram.
Right.
So I can't say that they're congruent because they're opposite angles or whatever. And I see that there are some angles labeled in the picture, angle 1 and angle 3. And those are opposite angles.
Right. And the fact that they have those marked in your picture probably important.
Yeah,
right?
we're probably going to use it.
Notice they don't have any segments really. Like they have lots of things with angles marked.
Yeah.
And because we're trying to prove something with angles, we're probably going to be using the whole idea.
You're probably right. So can I just go ahead and say angle 1 is congruent to angle 3 because opposite angles are congruent?
Okay.
Now, there are other ways to go about this, but I kind of had that idea first. Because there's that theorem that says if a quadrilateral is a parallelogram, then opposite angles are congruent. So I know angle 1 is congruent to angle 3.
Definitely.
And why don't you label that in the picture so I think that's a great idea. Get an idea. Okay. Now, angle 1 and angle 3 are not even part of angle 2 and angle 4.
Not at all.
Okay, so here's what I'm thinking. I'm probably going to have to, I'm seeing corresponding angles. I'm seeing alternate interior angles. So the only way I can deal with that is I have to state parallel.
Right.
So if I go ahead and say, can I go ahead and say like segment AB is parallel to segment DC, and then the other sides AD and BC?
Sure.
Those segments.
And I don't know that you need both, but let's do it.
Okay.
AD and BC.
Yeah, and you may not need it.
Right. And what's the reason that we know those opposite sides are parallel?
That would be the definition of parallelogram.
Right. And guys, the only thing you're going to do with definition is to talk about opposite sides being parallel.
Yeah, exactly.
It does not tell us any of those properties. Those are all separate theorems.
And I do like what Ms. Hogarty said. She said, we may not need both of those, so it doesn't hurt to have it in there. And you might even find that you don't even need step 2. All right. It just really depends. Like, I just started thinking about it, so I wrote it down. Okay. We've learned by now that if you have extra stuff, if it's not wrong, it's okay.
Right.
All right. So let me feed off of, I know that, let's feed off of AB is parallel to DC.
Okay.
I can say.
Or transversal.
Oh, transversal. Let's do transversal AD.
Okay.
I'm going to say from that, I know that angle 1 is congruent to angle 4.
And what's the reason that 1 and 4 are congruent?
That's because of alternate interior angles.
Right.
So AIAT theorem.
Awesome.
AIAT. However I said that.
Yes. Now, that's not the only transversal.
No.
I have another transversal. And what if I use the transversal BC? Then what do you notice?
I could say in the same step, angle 2 is congruent to angle 3.
Because it's also based off of the alternate interior angle theorem. Awesome. Well, look at what I'm supposed to prove here. I'm supposed to prove that 2 and 4 were congruent. I have them marked as congruent. I haven't really stated that they're congruent
No.
yet. But hopefully now at least we have a vision of where we're going. Okay?
Okay, so this is what I'm thinking.
Yes.
I really haven't used step 2. I just threw it in there. So I look at step 2 and like the first part of step 4.
Okay.
And I see that they both have angle 1 in common. So I'm going to say angle 3 is congruent to angle 4 because of transitive property.
Wonderful. We haven't used transitive for a little while.
No. The other thing, if you're thinking this is also correct. If you look back at the picture at angle 3 and angle 4, notice those are corresponding angles.
Right.
Of the
Other
sets of parallel. So you could have said that those are congruent because of CAP.
Right.
Okay. So this would allow you maybe to do some less steps, and you'll see what we're talking about in just a minute. All right. So I've used that. Now I have the second part of step 4, and I can say angle 2 is congruent to angle 4 because of transitive again.
And you're pulling that from this step right here and this new step.
Because they both have angle 3 is in common.
And so that's also now, could I put that with the same step since it's also transitive?
No, because it depends on step 5.
Exactly.
So if, again, backtracking, thinking about what we did, is you really essentially don't need step 2 to say step 5 because you could have said angle 3 is congruent to angle 4 because of cap. And then had step 4 in there and then use transitive property. So you could have had a little bit less steps involved. One less step, basically.
Yeah. And it just depends on what you kind of see first. And there's not a wrong way to do it. There's just different ways to kind of approach that same problem.
All right, one more proof. So notice the given this time gives you 2 sets of parallelograms, but take a look at your picture. Notice how there are, I mean, to me, I see several different quadrilaterals.
I do
but
too.
they also have things labeled kind of nicely for you.
Right.
So make sure you understand which are the parallelograms that they're talking about.
Okay, so A, B, C, D, as you're looking at that, notice that's got a 1 and a 2 marked for their angles. That means I'm probably going to be using those. And parallelogram A, E, F, G has angles 2 and 3 marked, so I'm guessing that probably we're going to be dealing with some opposite angles on that one too.
They're kind of giving you little hints.
They are really guiding us on this one.
Yes. So let's think about the first parallelogram they're giving you.
All right. And I'm not going to worry about definition or anything because I see some opposite angles there. I'm going to mark that those two are congruent.
So I'm from say, that one, which angles are going to be congruent?
Angle 1 is congruent to angle 2.
And that comes from this first triangle,
First parallelogram.
Parallelogram ABCD.
Like me now.
I know. So that means angle 1 is congruent to angle 2.
Because
and the reason,
opposite angles are congruent.
All right, so we know that. Now what?
And I also, from the second parallelogram that they've given me, I also know that angle 2 and 3 are congruent for the same reason. So let's go ahead and just put it in there. Step.
And I might even label it. Notice one, they're labeled now.
They're all marked congruent, which I wanted to show 1 and 3 were congruent. I have it marked in the picture, but I haven't stated it. But that's a really easy one. I know that's a really easy one-step transitive problem because they're both congruent to angle 2, so therefore they're congruent to each other. So angle 1 is congruent to angle 3 because the transitive property.
So notice the two proofs we did, not super complex.
No.
Right? Using stuff that we've done before.
But using these new properties, these new theorems.